Almost good evening. I realise it's towards the end of a rather long day. So I'm hoping that the discussion we're going to have now about spallation neutron sources is not so heavy. So hopefully it should be reminding you of things you already know, or just highlighting some of the differences between the experimental techniques and science that you can do at a spallation source as opposed to a reactor source. Of course, we're next to the Institut Laue-Langevin here, the world's finest reactor source of neutrons. So hopefully what I'm going to be able to show to you is how spallation compares and contrasts with what you can do at a state-of-the-art reactor facility. Just a little bit by way of my background. So my name is Sean Langridge. I come from the ICIS neutron and muon source, which is a spallation source of neutrons. Has anybody used ICIS? I don't recognize anybody immediately. Sorry, you all have? Yeah, we have a handful. Okay, excellent. So actually they could give the talk rather than me. But if they don't want to do that, maybe I'll carry on. So this is my lab. This is the neutron source here. A lot like the campus here in Grenoble. We have a state-of-the-art neutron source. In fact, we have two target stations. We'll come on to that in a little while. And we have a third-generation X-ray synchrotron, namely the diamond X-ray source. We also have a lot of computing power, as you might expect at modern large-scale facilities, and a range of other things, including big lasers and so on and so forth. My personal background, so I've been coming to Grenoble for many years now. I started off as a stagiaire, working at the Institut Laue-Langevin, so a little bit younger than most of you will be at that point. I remember when I took a PhD, which was work at the ILL, but also in America, my supervisor wouldn't let me come on the Hercules course. He said it was too long and I get too distracted. So it's kind of slightly ironic to be here lecturing and for you to all be sitting in the audience at the Hercules course. So it looks like this at Rutherford Lab every day. It's a nice, nice bright weather, although if I'm truthful, I've just checked. It's completely grey. There's 100% cloud cover, so it wouldn't be anywhere near such a nice picture. Okay, so I guess like many of the lectures that you've heard in the school so far, what we're trying to do is to provide a unique and quantitative description of what are really rather complex materials that cut across all of the physical sciences and life sciences. And we want to describe those materials from the microscopic through to the macroscopic. So actually, a lot of the science we want to do, we want to study many length scales. So hierarchical systems, multi-scale problems. So we'd like to have a probe that gives us access to many length scales. Neutron scattering actually can do that, and that's one of the key advantages, as you'll see, of spallation neutrons. It allows us to cover a very broad spectrum of parameter space. Okay, and mapping onto length scale, we also want to monitor them on a wide range of energy scales. And you won't be disappointed to hear that we can do this with neutrons as well. So we have unique probes that gives us a characterization of the relevant length scales and also the relevant energy scales. And if you can do that, then maybe you get a complete description of materials and you can describe their functional properties and so on and so forth. So this is a far too ambitious list of points that I'd like to cover, but you've got all the slides. I might update them because I did a little bit of tweaking on the way over. So we'll start by giving you a reintroduction to the neutron and why it's interesting. You know all this, so, but it does no harm just to go back and reiterate some of those. And then I shall explain about how we produce intense beam of neutrons. I'll also mention muons. Do muons come up in the Hercules school? I'm not sure that. Okay, I'll just mention them briefly because those are another thing you can do very well at a pulse source. And then we're going to compare some of the new developments between existing sources, which are typically called short pulse, and I'll explain to you what that is, and the next generation sources such as the European spallation source, which is under construction at the moment in Sweden, in Lund, which is a long pulse source. So we'll explain what that is, and actually I'll give you some examples about how the two compare. I won't say too much other than about compact sources. So these are all very large facilities. These are all kind of multi-billion euro investments in science. But actually, there's a really strong case that as part of the ecology, if you like, of neutron sources, we need to have a range of smaller sources that can provide a whole load of capacity and training and so on. And maybe compact sources are the answer to this, so we'll just say a little bit about that. And then we'll just go through some of the techniques that hopefully are relevant to you in your research and your future career, namely diffraction, reflectometry, small angle scattering, say a bit about spectroscopy, and just an interesting thing that we're doing at our lab with respect to high energy irradiation, which is totally distinct from all the other things, which in itself makes it interesting. And finish off with some summary and some future directions. So the key point is that with spallation sources, we want to have access to very intense beams of neutrons, and we want to have them over a wide energy or wavelength scale. Okay, because that means we can measure small amounts of samples, dilute samples, thin films, complex sample environments, but we can access a huge range of energy and time scales. Oops, is this working? No. Oops, sorry, computer's a bit slow. So just to reiterate, we want to provide absolute quantitative information. I think if you can do these measurements by any other technique, you should do. But if you really want absolute quantitative measure on both the structural, the dynamical, and the magnetic properties of materials, neutrons are going to be the way to do that. On a whole range of length scales and for a whole range of systems. I'm sure in this room there's people studying all of these things from powders, single crystals, single crystal heterostructures, and so on. Okay, so let's just remind ourselves about neutrons. So neutrons, uncharged particles, found them in atomic nuclei. Typically, they have velocities of about 2.2 kilometers a second, which means that if we're going to kind of start timing neutrons, and you'll see why that's important in a little while, then we need to kind of have millisecond, microsecond time resolution. And these same neutrons have a wavelength of about 1.8 angstrom, but vary, as you know. And what that means is that we can study a wide range of materials going from micron length scales right down to the angstrom with this amazing resolution, so femtometer resolution, which is truly phenomenal. And energy ranges that go from rather high, say 100 millielectron volts, down to the micro electron volt. So that's covering a huge range of energy and length scales with the same probe, if you like, but implemented in different ways. Neutrons are neutral, so they are very penetrating. That means we can use them to image materials, look inside materials. There's a lot of interest in cultural heritage, being able to provide provenance for artifacts. How were they produced? Were they consistent with the production techniques known at the time? And of course, we can do it non-destructively, so we don't damage the material. So if you're a museum wanting to have a specimen studied, we don't have to cut it up and damage it. The other important point of them being neutral and penetrating is that means we can have rather complicated sample environment, as you know. So we can go to very low temperatures, high magnetic fields, toxic environments, hydrogen environments, biological containment and so on. All of these things become a lot simpler because we have a very penetrating probe. So we can drive right into those materials and not create too much background. And this actually is one of the very significant points about neutron scattering, is that because we don't interact with the cloud of electrons as X-rays do, we interact with the nucleus with a strong nuclear force, rather than getting a scattering power that goes with the number of electrons you have. It varies kind of quasi-randomly across the periodic table, which means that we're able to see very light elements, such as hydrogen, in the presence of much heavier elements. So if you believe that a hydrogen economy is going to be one of the things that saves the planet, then neutron scattering is going to be a really good technique to tell you where the hydrogens, the oxygens are in your system. Okay. So that means we see the world differently. So we're all familiar with an X-ray image where you get dominated by the heavy things like the metal here. Neutrons are going to see the world in a slightly different way. So if you were to take the same image, which I took from PSI, if you took the same image and took it with X-rays, you would be dominated by the very heavy things, so the metal that contains in the camera. But you can see the neutrons, they sort of see everything within the sample. And that's true on the macroscopic scale but also true on the atomic length scale. You'll also be familiar that because we scatter from the nucleus, the scattering length depends strongly, or can depend strongly, on the isotope, and we have this rather beautiful reality that hydrogen and deuterium have vastly different scattering lengths, even a different sign. I don't know if anybody can explain why they have a different sign. But that means that if we can substitute hydrogen for deuterium, we can do very clever separation of the scattering, if you like. So the different parts of the sample will scatter differently depending on whether they have hydrogen or deuterium, and this allows us to do, this is a case of low to medium resolution small angle scattering, where one takes the atomic structure from X-rays of this particular system, deuterate it, different parts of the molecule, and you can get a really accurate description of a material in solution that you couldn't do with any other technique. The other point is that neutrons are a spin-half particle, so they have magnetic moment. So you can study microscopic magnetic structures, we can study magnetic fluctuations, we can form polarized beams, and that will be the topic of the lecture tomorrow. And it means we can study nuclear structures, magnetic structures, and we can play some nice tricks to separate coherent from incoherent scattering. So those have all been techniques that we can apply neutron beams to give us new information. I just have one slide, because I think personally I find it really interesting, that actually just studying the properties of the neutron itself is amazingly valuable, and one thing that's done very successfully here at the ILL and also at PSI, two particular things which are, I think the phrase is discovery class science, so these kind of things that lead to Nobel Prizes, is one is does a neutron have a dipole moment? And the prediction is, well, the level that can be measured at the moment is like having an electron and a proton separated by the diameter of the Earth. That's the level of the measurements at the moment. And more interestingly, in my view, how long does it live outside the nucleus? And there's an interesting anomaly, because if you measure it in two different ways, if you measure it through looking at decay from a beam of neutrons, or you put ultra-cold neutrons in a bottle where you store them, you get different lifetimes. So it's about 15 minutes. But you find the two techniques give you a 9-second difference between the two probes. And so there are lots of ideas as to why this is happening. Some include dark matter, that you're losing neutrons that go into dark matter. But it's still not resolved, but clearly hugely interesting. But let's get back on track. So these are the length scales and the energy scales that we've been talking about. So on the length scales, we know that we can image macroscopic objects on the centimeter-meter length scale. We can go down looking at things like cell and membrane structures in reflectometry small angle scattering, magnetic domains, polymer structures, magnetic structures, and so on. And on the time scales, we can image things on the second time scale down to lattice vibrations and spin waves, 10 to the minus 12, 10 to the minus 13 seconds. So we have access to a huge range of energy and timescales. And this is what spallation sources do so well, as we shall show. Another way of thinking about this is actually plotting time along this axis, wave vector along here, real space length here, so energy, space. You can see that neutron scattering actually covers a huge area. So here we have spin echo. We'll talk about that briefly tomorrow maybe. Time of flight spectroscopy, which is what we're going to be talking about, high resolution backscattering, and so on and so forth. So you can see with our range of techniques, imaging at the macroscopic, SANS for nanoscience, diffraction for the atomic scale, we're able to see a huge range of energy and length scales. Okay, so let's start off by talking about reactor neutrons. So I'm sure you're all kind of familiar with this. So fission was discovered in 1938 by Lisa Meitner and Otto Hahn, where they irradiated uranium with neutrons. And I'm sure you're familiar with this process here. You take a heavy fissile atom, so uranium-235. It absorbs a slow neutron, which is slowed down with some moderator material. This breaks up the nucleus into a whole range of smaller fragments. But what you find is when you look at the fragments, there's a small amount of mass is actually missing. Okay? So about 0.1% of the original mass is missing. But through Einstein's relationship equals mc squared, that corresponds to a huge amount of energy. And of course, that is why nuclear reactors are so efficient at producing heat that we can then use to produce electricity. But they're also very good at producing large amounts of neutrons. So for every U-235, you end up with about 2.5 neutrons and a lot of heat. So this heat is good in some ways, but if you want to do research with neutrons, you don't really want this heat. You'd like to get this figure down. So typically at the ILL, when it was running, I'm old enough to remember it was running at 58 megawatts, you'd have something like 10 to the 15 neutrons per square centimetre per second. But the ILL is almost certainly the pinnacle of what we can achieve with reactor sources. This is an old image that I found of the Advanced Neutron Source, which is a proposal in America. So the kind of supremacy in neutron science has kind of moved across the Atlantic at different periods of time. And this is part of the Americans' response to try and move the centre of mass from Europe back to the US, which is a proposal for a 350 megawatt source. ILL 50-something. It turned out it was too good to be true. The engineering complexity of a source this large, the cost and so on, just didn't make any sense. So the ILL is probably the pinnacle of what we will achieve with reactor-based sources. There's also the other problem that to get a nice compact core in a reactor, you typically want highly enriched uranium. So you want lots of uranium-235. That's a problem because of proliferation. So basically that's weapons grade material, and you don't really want that. So there is a lot of activity to actually replace these highly enriched sources, greater than 90%, down to low enrichment. So a reactor, what did I write down here? Yeah, a reactor typically 90% enriched. A power reactor, 4%, okay? But they don't have the same constraints. We want a nice, bright source of neutrons. So actually, there's quite a lot of interest, this is 2016, in trying to move from high enrichment to low enrichment. And there's also the whole socio-economic issues around reactor sources. And many countries in Europe have decided they don't want nuclear power, for example, and so on. So what's the alternative? And the alternative, hopefully we'll show you, is going to be spallation. So it's important just to understand the flux distribution so we can compare it between the two techniques. So this is typically what you see from a reactor. So you start off by seeing a fast so-called Lamb distribution of neutrons at about 1 to 2 MeV. So remember that number. So big for a reactor is 1 to 2 MeV. Then these slow down. This 1 over E intermediate distribution, so-called epithermal. And then if we have some moderators, we can slow that down to the milli-electron volts. So remember, milli-electron volts are the typical energies of excitations in condensed matter, or in wavelength, the typical length scales that we would expect to see. Okay. There are lots of code, if you want to go and look out there, to allow you to simulate the performance of reactor. I think Géant is the French version, MCMPX is the US one, FITS is the Japanese code. And all these codes allow you to actually go and predict the performance of a reactor, but also of a spallation source. So let's get to spallation. We start off with a proton, but as you see, it's very high energy. Okay, so at the Rutherford lab, we operate between 700 and 800 MeV. So remember, reactor 1 to 2 MeV. Here we're talking about 800 MeV. When I talk about the ESS, I'm talking about GeV. Okay. And the point is, we're going to produce neutrons up to that energy. So we're going to have a lot of high energy neutrons. So a proton comes in, we hit a heavy target nucleus, which is a heavy metal, tungsten, lead, uranium is another option. This then gets absorbed. There's a whole range of internuclear cascades. And so it's like the nucleus gets very excited, it starts to boil, and it kicks off a whole range of particles, of which a lot of them are neutrons. So for every collision of the proton, we get about 16 neutrons come out. Okay? And the amount of energy we get is only about 20 MeV per neutron. So remember, like a factor 10 down on what you get with a reactor source. So this is good. So we're not going to be generating huge amounts of heat that we need to get rid of. Okay? So here's the energy. This is just some old data. I can't remember where it was taken from. Number of neutrons for a range of different targets. So in this case, uranium and lead. So uranium is very nice. It gives you a large flux of neutrons, but it has some other problems, and there's delayed neutrons and so on. So we don't use lead, even though it would give us the biggest flux of neutrons. So at my lab, we use tungsten clad in tantalum, and the ESS we use tungsten, as you shall see. So how do you do this? Is this going to work? Movies never work, do they, in these things? Oh, hang on. Okay, so we start off with an ion source. So we produce H- ions. Okay, we've missed that bit. They're now into the linear accelerator. So these get accelerated up to about 665 keV. They then get bunched up, and then in an RFQ, they get accelerated even further, up to 70 MeV. Okay, so by this point, as we go into the ring, 70 MeV. Okay, so that's something like 37% of the speed of light. We take a small aluminium oxide foil, which strips off the electrons, and we inject the protons into our accelerator. Okay, so we're now injecting protons, and we get as many protons in as we can, up to the space charge limit, because they don't like being together. And I think it's something like 10 to the 13 protons inside the ring. They then get accelerated up to 700 or 800 mega electron volts, and they do something like 10,000 turns of the synchrotron. Okay, they get bunched up into these two kind of salami sausages, and then do around 10,000 turns. That's a technical term, by the way. They do about 10,000 turns of the machine, and then by using a high field magnet, we can ramp from 0 to something like 5,000 amps in 100 nanoseconds. That kicks the proton beam out of the ring. Then by a series of bending of focusing magnets, we can drive it down to the target station. And there's a muon source on the way, so we hit that first. Come back to that in a second. And then we hit our heavy metal target at the end. And we generate a burst of neutrons that goes out to a whole range of instruments. And we do that at 10 hertz, 50 hertz, kind of whatever. And we'll come to see the importance of that. But you can also see from that accelerator that if you bring out different lines of proton beams, then you can run different target stations. Okay? So that's what we do at our lab. We run two different target stations with different characteristics, and you'll see why that is the case at the moment. I said that we're doing this 50 times a second. So as you can imagine, this is really quite a complicated operation. So I'm continually amazed by our engineers who are able, and technical staff who are able to keep the facility running, given the complexity of this. A reactor, within reason, once you've got it going, then the easiest thing is just to let it run. For us, it's really quite a challenge to maintain these sources. But a modern source will give you availability of well over 90%. So it's pretty much on all of the time. Okay, so let's have a look about how neutron flux has changed over the years. Was the previous talk about exfel? Just okay. So this is neutron flux. Okay, neutrons per square centimeter per second. So this is Chadwick discovering neutrons. So we'll call that 1 neutron per second per square centimeter. Interestingly, Chadwick thought that neutrons would be of no use to society beyond just the fact that you've discovered another particle. So in many ways, we're proving Chadwick wrong, at least on this one point, that hopefully neutrons are useful. So this is in the 1930s. And actually, maybe I'll try and find the reference for you. Just show, he writes this discovery in a letter to Nature. It's only a few hundred words, a single page. I mean, I imagine you're writing sort of 10, 20-page articles now, many thousands of words. Single letter to Nature and a neutron prize in 1938 for the discovery of the neutron. Different world. So let's run forward to the 1940s, and we start to have the first fission reactors. There's the Chicago pile, Enrico Fermi, and so on. So rather rapid increase in the flux. So let's look. This is in 5 orders of magnitude, 5, 10, 15. So you can see here from CP2 up to the ILL, we've jumped up about 5 orders of magnitude in the space of about 60, 70 years, something like that. Okay? But you can see it's kind of flattened off. So this is the ILL, this is the high flux beam reactor. These are US sources. Okay? So fission is really good, but it's also really good at producing heat. So actually, if we wind forward to the latest sources in Germany or Australia, you can see that we haven't really changed the effective thermal flux. That doesn't mean there's not been progress, or of course there's been huge progress in what we do with those neutrons that we produce, but it's just to make the point that we're not seeing the huge ramp up in flux that these guys see. So this is a plot of generations of X-ray sources, so I'm just about old enough to remember working at second generation sources in the UK. I worked at the ESRF here, so that's third generation sources, and now free electron sources. And just look here, we're now, if this is 10 to the 10, so if I started my career at 10 to the 15, we're now on at 10 to the 35 or something. So the number of photons that you have access to is absolutely phenomenal. But we're not seeing that with neutrons. But there must be a good reason why neutrons are so useful if we're not seeing this big increase, but we're still wanting access to neutrons. So the thing that sort of slightly changes is to then move to accelerator-based sources. Okay, so here's from the various earliest sources in Japan, in Argonne National Lab in the US. Our facility is here. The SNS in Oak Ridge in Tennessee is here. JPOC in Japan. The new source which is coming online, CSNS. So these are all short pulse target stations, and here we have ESS, which is the long pulse target station, and we'll come back to that in a little while. Okay. Now you can argue, where these numbers are, but basically the trends are there. And the thing that we're going to see with accelerator-based sources is that they're scalable. Okay, so one of the things is it is relatively easier to put more power into a target. So we understand accelerators, synchrotrons, linacs, and so on, and we can get ever-increasing amounts of power, which gives us other problems, which you shall see. But it looks as though our reactors have kind of stopped here. And so actually, to move this on even further than ESS, we're going to even need new technologies, which we may touch on at the very end. I'm not going to say too much about PSI. PSI sits somewhere in between. It's a pulsed reactor, has an accelerator based on cyclotrons, but it runs at very high frequency, so it makes it look a bit like a reactor. Okay, so this is just a slide I stole from PSI, where they run with a lead zirconium. So you're getting familiar with this now, lead target. They also ran with some lead, liquid metal lead bismuth eutectics, which is pretty successful. But they typically run now with lead zirconium. In fact, they're not running at the moment because they're in the middle of a big shutdown, and they'll come back online next year, I think it is, after a major upgrade to the guides on their beamline. So they should come back with big performance upgrades. I just show this particular slide because here's the neutron source, but this is one of their experiments to measure ultra-cold neutrons. So here's one of the bottles I was talking about. This is where they're storing ultra-cold neutrons to measure the neutron lifetime. Okay, so let's just take a moment just to compare pulse sources against continuous sources. So for a reactor-based source, you see that we expect to have a large flux of low-energy neutrons, okay, intrinsically. And for the pulse source, we'd expect to see a large flux of high-energy neutrons that we're going to have to slow down potentially to make them of use to us. Because you have a lot of low-energy neutrons, it makes it relatively easier to shield. So it's easier to stop low-energy neutrons. The counterpoint, I guess, to a pulse source is actually, if you think about the animation we had for the ICES accelerator, actually when your neutrons hit your sample and then your detector, the machine is basically switched off. And then it ramps up again to give you another pulse of neutrons. But when you're measuring, the machine is switched off. So you have very low backgrounds on a pulse instrument. You can get to very high peak power. So, we said there was a difficulty in going from 50 megawatts, 58 megawatts up to 350. Actually, the ESS, as you shall see, is going to run at 2 megawatts. our second target station runs at 40 kilowatts, so it's relatively easy to get high peak power. Okay? And you can get the peak power so big and the repetition frequency high enough that then the integrated power should become, and therefore the neutron flux, should become comparable to what you can get at a reactor source. You can make the pulses of neutrons very sharp, which means you have high resolution. So if you want to do high resolution diffraction, for example, then you want a sharp pulse from your accelerator. We'll see how that works. Downside is, certainly in case of diffraction, is the pulse shapes are often asymmetric, as you'll see. They're not nice Gaussian shapes, so your resolution convolutions and so on can be a little bit trickier than you might expect. But we sort of know how to deal with that. The wavelength band that you can observe, so your ability to look over multi-length scales, multi-energy scales, is controlled by the source frequency, which is something you control, so you can design that. It probably has a lower environmental footprint. I mean, these machines consume huge amounts of energy, so there's a big issue there, okay? But actually, they're not nuclear facilities. When you turn them off, the decommissioning is easier. So unlike a reactor, which has an environmental footprint, it's arguably lower in the case of a pulse source. And we know that this is the most efficient process for neutron production, basically because we're not dumping all that extra heat that you get from fission. We don't have such a broad problem, a big problem, sorry, for pulse sources, and they intrinsically, naturally, give us this very broad range of energy and wavelength, as you shall see. So actually, we're very privileged. You're very privileged because you have access to both, okay? And they very much are complementary. So in choosing the kind of instruments you want to use, the source you want to use, often it's quite clear which one you should go to. And maybe that will become clear as we move forward in the talk. So I said I'd say a little bit about muons. So is anybody doing any muon spectroscopy as part of their thesis research? Okay. Is this PSI or us? ISIS, okay. So muons are these exotic particles, about 1/9 the mass of a proton, about 207 times the mass of an electron, and we produce them quite straightforwardly by putting a carbon target in the proton beam. So if you remember, when the proton beam was heading towards a target to produce neutrons, it hit an intermediate target, which is a carbon foil. That absorbs a few percent of the beam, doesn't take much of the proton beam out. And when that happens, it produces a pion, which decays into neutrinos and muons, and the muons are 100% spin polarized, okay? So as you'll see tomorrow, we have to go to a lot of trouble to polarize neutrons, whereas the muons come out 100% spin polarized. They don't scatter from material, you implant them in material. So a muon comes in, gets implanted in the material, it starts to process around the local field, and then 2.2 microseconds later, sorry, it decays into a positron, some other neutrinos, and we detect these decay positrons, okay? And from that, we can then build up a picture of the local field that the muon must have seen, okay? And that field may vary at different sites in the system. And the way this works is that the positrons that we detect are preferentially emitted in the direction the muon spin was pointing at the time it decayed. Okay, so if you measure an asymmetry, if you put a detector, say, at the back and the front of your sample and measure how that asymmetry changes with time, then you can build up a picture of the local structure. And you can use that to study a wide range of systems. Superconductors, so looking for exotic time reversal symmetry breaking superconductors is one of the technique's great strengths. Looking for various ionic conductors, so there's a lot of battery research that's done now. As well as some fundamental science related to the science of the proton. But there's also a kind of a new and interesting development, is that the muons that were produced here were positive muons. Okay, you can produce negative muons, which nobody really cared about too much because they thought they'd just go in, would just crash into the nucleus because of the charge attraction, and that'd be the end of it. But what happens is that as they do that, they generate a whole range of high energy X-rays, and here's the energy of those X-rays as a function of the atomic number. And for anything above lithium, I think it is, you can see you get very characteristic energies that you can use to image. So you can bash these muons into a material and start to image elementally image what's going on. So rather new and interesting development. Okay, so this is just summarizing the energy spectrum against flux for the two techniques. Okay, so this is our steady state neutron source, kind of sort of schematic, low energy, and then we have this pulsed nature, which is not shown here actually, but the energy profile is going to look something like this. It's pushed up to higher energies. And of course, the trick we're going to play is that we need to take our steady state source, so this is the ILL as a function of time, and replace it with our pulsed neutron source, where we're going to be hitting the target at some particular frequency, 10 hertz, 20 hertz, 60 hertz, and so on. And so you can see that the repetition rate is going to be important, because obviously if you shorten that time out, you can get more power onto the target, okay, by having more of these pulses in here. But what you'll see later on is you've got less neutron bandwidth if you do that. But also you've got some materials challenges, because you're dumping so much power into the target so quickly. So this is one of my rubbish animations. I do apologize. So this is how time of flight works, okay? So here's our target. Okay, here's our detector. Our proton beam is going to come in from the top. And this is really the natural choice to make measurements on a spallation neutron source. This idea that you've got a pulse beam, so you know distances, you know angles, and you know time. You know, neutron detectors are energy insensitive, so we can't intrinsically measure a neutron wavelength, but we can measure a time, and if we know distance, then we've got its energy and its wavelength. So target, yeah. So as I said, thermal neutrons, sort of kilometers a second, so millimeters per microsecond. So we're going to be wanting to time in on microseconds. So let's add our sample, which is here. Here's our moderator. Okay, proton pulse comes in, big burst of neutrons. Okay, moderated here. We'll say a bit about moderation in a minute. Into the sample and into our detector. Okay. Oh, let's go with that again. Does it work again? Well, there we go. Beautiful. So that's a diffraction experiment. Very straightforward. Let's have a look at a little bit more detail what those target looks like. So this is the existing target on TS1. Okay. So this takes 160 kilowatts of proton power. Okay. And what it consists of are blocks of tungsten, which is the dark grey here. It's in tantalum clad, and these little channels you see here are for cooling, and the little holes are for thermocouples. Okay, so proton beam comes in here. Actually, it's probably half the size of that in reality, something like that. So that's the existing target station that is beaming away as we speak. Actually, we're in the middle of a new project which will start next year. 4th of January, we'll start a new TS1 project where we'll replace this target with a much smaller one. But this is what we have on TS2. So the TS2 target, again, is probably a factor 2 smaller than that. But you can see it's large. It's a single block of tungsten. Proton beam comes in here. Tantalum clad, and then we have some cooling on the side and on the face. So whilst this is 160 kilowatts, this is only 40 kilowatts. But actually, for certain classes of instruments, one can get more neutrons out of a 40 kilowatt target than you can out of 160 kilowatt. And we'll come on to that in a little while. So you surround your target with reflector. So having produced all of these neutrons in the target, you moderate them, you slow them down. We'll talk about that using hydrogenous materials. But you also want to reflect them back in to give them another chance to moderate. So you know there's not really a preferential direction in which the neutrons are produced, so they're going off in all random directions. Unlike a third generation X-ray source, you've got a nice coherent beam, very low emittance, very low divergence. The neutrons are going everywhere. So we want to reflect them back in, so we take a nice light material like beryllium. So this is a drawing of the TS1 reflector. This is what we're going to replace it with next year. And that's basically from the lessons we learned on TS2. So basically inside of here is is beryllium as a reflector, and I'll show you the view inside in a little while. Okay? And these apertures are where the beam ports are going to view. Okay? So all of the neutron instruments are going to be viewing in here, or in here, or in here. And they take a view of the moderator, not the target. The target just gives you a lot of very high energy neutrons. The moderator gives you the thermal, cold neutrons, epithermal neutrons, the ones that you actually want. So this is the target station installed in position. So you can see this is just the manifold, if you like. Proton beam comes in from this side. So that diameter is something like that. And in our case, we've got these 12 plates of tungsten, which are all electron beam welded together. So it's kind of a bulky thing, and that's what we're trying to reduce the size. Why do we want to reduce the size? Because that makes a brighter source. Okay, if we can get everything to be more small and compact, then our brightness will increase, and hopefully at the same time maintain the same level of absolute flux. So this is how it looks on the second target station. So let me just talk you through this. So there is the target there, okay? So that's the cylinder about so big. Proton beam is going to come in this direction, hits the face of the target. Above and below these containers that you can see there are the moderators, okay? So here we're going to be producing neutrons of energies up to 800 mega electron volts. We need to slow those down through moderation, so we take a series of hydrogenous materials in these cans at various temperatures. They thermalize or partially thermalize with those moderators, downshifts the energy into the millivolt scale or whatever we need. This is all beryllium. Okay, in our case it's nickel coated, so you can't actually see the beryllium, you just see the coating. And it's sort of like a clamshell, it kind of opens up. This is for maintenance. Okay, so actually in reality when this is in operations, those two things close together, so there's not a big gap here, and all you just get is the hole, okay, into which the neutron beam goes. And this means you can get a very compact target, get your moderators in nice and close, and that leads to nice, bright beam of neutrons. And that's why on the second target station we can get these very large fluxes of neutrons, is because we can make everything small and compact and close together. That's not to say you don't have materials problems, and one of the biggest problems is, I'm sorry about the resolution here, is basically the stress that you place on your target. So if you imagine you're being hit with 160 kilowatts 50 times a second, your thermal variation is going to give a lot of fatigue and stress cycling in your target, and so you need very good engineers who can predict and model how this behaves. So this is really one of the significant challenges now of accelerator-based sources, is even though I've said our heat production is relatively low, the amount of power that we're putting onto the target in terms of proton beam is really rather high. So this is our big challenge. Okay, so let's say a little bit more about the moderator. So here's our reflector. There's a target in the middle. You can sort of see some moderators here. This one's got two different sides. Okay, this is this is a grooved moderator. So there's a reentrant hole here. This is a flat face for different characteristics. Here's our moderator. So let's have a look at the intensity that we see as a function of time. Okay, so proton beam comes in, bright burst of very high energy neutrons. Okay, and then slowly they start to thermalize in the moderator, and so as a function of time we see this level drop out, and so you can see here I've got this asymmetric shape, which is one of the challenges that I mentioned when it comes to resolution calculations and so on. So actually the material that this is made of, the temperature it's at, and the physical shape are all going to change the properties of the pulse width. Okay, so if you want to tune this pulse width and shape, there's various things you can do with the moderator: change its thickness, change the way that it's coupled, and so on. So here's the energy spectrum for our three moderators. Okay, liquid hydrogen, liquid methane, and water at three different temperatures, and you can see here that this allows us to tune the energy that a particular neutron beam line views. Okay? Now you can't readily change the moderator for an experiment, so you sort of have to choose one and then you live with it until you decide to change something significantly. So if you want to look at a high energy beam line, to look at high energy excitations, you want to be on a water moderator. If you're after cold neutrons for nanoscience, then you want to be on a liquid hydrogen moderator. So these things are very difficult to change, but you can do it, and we'll see that a little bit later on. So this is the flux profile we see. We see this huge flux close to 0 time. Okay, so that's that initial burst of very high energy neutrons, which decays down. And then we start to thermalize and moderate the neutrons. Actually, we don't moderate them fully because the moderators in a way are rather leaky. So they under-moderate, but this is the kind of spectrum we would expect to see. So very bright burst, and then this is the spectrum that we're going to use to make our measurements with. So here's some calculations. This is on the second target station. So here's the time, microseconds after the initial pulse of the proton beam. You can see here is this very rapid rise, and then this decay. Okay. So this says decoupled, and what that means is you decouple a moderator from its surrounding reflector. Okay, so the neutrons come into the moderator, they get 1 or 2 chances to slow down in the moderator, a few collisions, and then go straight out down to your beamline. Okay, so you get a pulse that's sharp. Is this making sense? You get a pulse that's sharp, but you don't get so many neutrons because they haven't had much chance to live in the moderator. If you put some reflector around them and give them a chance to go back into the moderator, change their mind, thermalize, and come out, then you coarsen the time structure, okay, but you gain some neutrons. So part of the challenge in the design of neutron instruments is how you play around with this flux resolution, because this is going to be intrinsically a lower resolution instrument than this one, but you've got more neutrons. Okay, so if you're into a moderate or low resolution technique like SANS, for example, you probably want as many neutrons and you don't care about the time structure too much. If you want to do high resolution diffraction, then actually it's the time structure here is probably the most important thing. You would take time structure over flux, whereas these guys would take flux over time structure. So often competing demands. And this is how the full width half maximum of this function changes as a function of wavelength, okay, for the different moderator faces. So you can see not only does it depend on the moderator, but it also depends on the wavelength. Okay, so those slower neutrons are going to spend a lot of time in the moderator, which is going to give you a very broad full width half maximum. Okay, but note these timescales were down in the microseconds. When we get to ESS, we're going to be talking about milliseconds. So this is what we call short pulse sources. Okay, so just to show you the kind of flexibility of that before we have a short break. This is the ISIS neutron source. Here are the 2 target stations. This one was opened in 1986, this one in 2009. This runs basically at 40 hertz and this runs at 10 hertz. So this is high power, this is low power, this is high resolution, this is medium resolution. And what that means is you can have a whole spectrum of instruments, okay, which cover a whole range of science. We have 30 odd instruments. It varies from day to day how many instruments we have, for a whole range of science that you get from an accelerator-based source, because you have this ability to tailor the target stations, the target, the rep rate, the power, the moderators, to give you these different characteristics. So that pretty much concludes what I'd like to say about short pulse target stations. Okay, if we take a 10-minute break now, then we come back, we'll talk about long pulse target stations, we'll compare and contrast, and then we'll give some examples of just what that means in terms of instrumentation and the measurements you can make. Okay, so we come back in 10 minutes. Thank you. Many of you will have the pleasure of using the ESS, the European Spallation source. So this is, I think it's probably the biggest science project in Europe at the moment, and when I say big, this is how much it costs. I'm very familiar with this. I have a long engagement with ESS. So this is 1.8 billion euros. So you would hope that you get a lot of science out of such a facility, and in 2023 we will find out. Yeah, it's going to be great. So this is the ESS. Let's just look at some of the numbers. It's going to be 2 GeV. So remember, we were 800 MeV. So more power, more neutrons, but it's not entirely linear. So there's a kind of sweet spot to find between the proton energy and the neutron production. Relatively low frequency, 14 hertz, and we'll see about that. But look at the pulse length. Okay, this is 2.86 milliseconds. Remember I was talking about things that were microseconds? We're now just making this really long. Okay, so we should talk about why that's relevant. We're going to have 2 megawatts average power. Okay, the peak is probably 100 megawatts, something like that. But on average, about 2 megawatts. And the way to deal with that is to have a solid rotating tungsten target. Okay, and we'll see about that. This is going to be something that's like a couple of meters in diameter. It's going to rotate slowly in the beam. Okay, because you're dumping 2 megawatts of power into it, and it's going to be helium cooled. And eventually, we're going to have something like 22 public instruments. So this is a very nice example of Europe coming together. So this is a collaboration with a whole range of European countries. So it is being hosted by Sweden and Denmark. It's been constructed. Any guys from Lund here? Yeah, excellent. Very nice university town in southern Sweden. Very easy to get to. There is some bridge, takes you across from Denmark into Sweden. So it's a very nice place to be. So this is essentially half of the construction cost will be made by Sweden and Denmark. So that's all in real money. And then the other half comes from the partners. Here's some of them listed here. Sweden and Denmark, very cleverly, will only contribute about 20% of the operations, and the other member countries will contribute 80%. So this is a big European project. Okay, so for 1.8 billion euros, you expect some amazing things. So let's have a look. So this figure shows time in milliseconds across the bottom against brightness. Okay, so brightness, if you're not familiar with the term, so here's our flux that we've been talking about, neutrons per square centimeter per second. But if you then look at per steradian per angstrom, that's a much tighter measure, if you like, of your source. So it's telling you about the degree of divergence, the energy per unit energy, or in this case per angstrom. And this is where we are with our existing sources. Okay, so here's this is TS1, it's down here. Okay, this is our short pulse. We're something like 140 kilowatts now, so it's increased a little bit, but not by much. Here's TS2. See, it's lower power, but because we can make it nice and small, the brightness is higher. So even with a 40 kilowatt source, the brightness is higher. Okay. Here's SNS, which is the Spallation neutron source in Oak Ridge. Currently running at 1.2 megawatts. Okay, it's down here. This is the predictions for J-Park, and here's the ILL constant of 57 megawatts. So this is ESS 5 megawatts. This is the brightness for 1.5 angstrom. And you can see that what they've done is to just extend this pulse from microseconds up to milliseconds timescale. Okay, so this is enormous. Okay, so you can see the massive gains in brightness. That's a 1.5 angstrom. If you look at 5 angstrom, it's a rather similar picture. So this is the initial design, actually, in 2015, was at 5 megawatts. And then around that period, 2017, something like that, a decision was made that actually let's go with 2 megawatts to start with. Okay, and that's going to save you money on the accelerator, so you can have less accelerator power, but you build everything up assuming that you go to 5 megawatts. So, okay, that might seem a little bit disappointing. So 2 megawatts, you're going to have fewer neutrons, but actually you win it back with moderators, as we'll see in a little moment. Okay, but you can see we still have something that is hugely impressive in terms of neutron production. So what's the challenge? I mean, why do we have short pulse? I mean, why do we ever have short pulse? Why don't we just go through the long pulse? And we try to capture that on this slide here. So here are this is a short pulse. Okay, so you start with an intrinsic short pulse onto the target, and then your moderators then essentially choose your pulse width, So here's a decoupled, so you remember that, so medium flux with a medium resolution. If we couple it, we increase the flux, but we increase the time structure, so we lower the resolution. Or we can do something called poisoning, which is where we deliberately put some absorbing material, cadmium, gadolinium into the moderator, that effectively makes the moderator smaller size. Okay? So it's smaller size, so the time structure sharpens up, but the flux lowers down. Okay? But straight away now you can see, well, with ESS, what's going to happen with your resolution? Because we've got this enormous pulse. Okay, so how do I know when a neutron is produced? Because it could be produced at any point in this 3 milliseconds. Okay, and because I'm measuring time of flight, I need to measure time accurately and distance accurately. I can measure distance, but for time, if I'm not sure when the neutron was produced, then I don't know what the time is precisely. So I'm going to get a huge uncertainty. So in this case, you can see it'd be relatively short, because it could be produced here or here, sort of order 100 microseconds. Here we've got milliseconds, okay? And the way we get around that is to use pulse shaping choppers, okay? So we're going to use the chopper device, which is just an absorber that basically opens and closes in a well-defined frequency and phase to actually cut out certain parts of the pulse. If we don't cut out certain parts of the pulse, then we're going to have a lot of neutrons, we're going to have relatively low resolution, okay? But with pulse shaping choppers, we can pull back that resolution. So how does that look? So this is a time distance diagram. If you've not seen them before, they're relatively straightforward. So time is running along here, and here is the pulse from our source. Okay. So tau here for ISIS would be microseconds. For ESS, it's going to be milliseconds. Okay. So then we allow distance to run up this way, and so here, let's say we put a detector at this point here. Okay. So you can see that we're going to produce this burst of neutrons, and so the slow neutrons will take a long time to get to our detector, and the fast neutrons will take a shorter time, and so this is going to be our wavelength band. Okay. So we're going to put some aperture here. This is our chopper, which opens once for every pulse. Okay, and so we can put that at a certain distance, L1, and we can put our sample or detector at a different distance, L2. Okay, so this is basically the time we have to make a measurement. So that's going to depend on the rep rate of the source. Yeah, so if I run at 60 hertz, I'm going to have far less time, because if I do that, this gets shorter. If I don't know anything about it, then the next pulse comes along and you get overlap between the two pulses, the different frames. Okay. If I run it slower, then I get more time, but I guess less power into the target, so fewer neutrons, but over more time. So there's a compromise to make. Okay. But so in the case of ESS, this is the 14 hertz, which is roughly, I think, 70 milliseconds, something like that. This is the 3 milliseconds we were talking about, 2.86 milliseconds. So if I just take the ratio of those two things, this time over this time, I get 25. And that tells me if I make the distance L2 over L1, should also be 25. Then if I make L1 about 6 meters, why is it 6 meters? That's about as close as you can realistically get a chopper to the target, okay? Because you've got shielding, you've got shutters, and so on. So that's the closest you can get. L1 is about 6.3 meters, okay? And that tells me L2 should be 160 meters, okay? So if I have my instrument about this long, if I make L2 about 160 meters, you can see that I very efficiently use the entire frame. This is sometimes called the natural length of the instrument, because in this geometry, I fully fill the frame before the next pulse comes along, and so on and so forth. That's a very efficient way to do that. Okay. If I want to, I can calculate what wavelength band this actually lets through. Okay. So it goes as the distance, L2, and the time I have available to me, so the rep rate frequency. And in this particular case, we'll come back to this later, you have a wavelength band of just shy of 2 angstroms. Okay, so you have a relatively short wavelength band, 1.8 angstrom. If you slow down the accelerator, that gets bigger, sorry, the rep rate. If you increase it, it gets shorter. You can play the same tricks that we talked about earlier on. You can have moderators with different temperatures. Okay, so a water moderator and hydrogen, and that's what ESS will do, have two moderators. And again, you can use your pulse shaping choppers to select out particular wavelength bands that you require. And then, of course, if you put your sample, let's have this natural length of the instrument, put a sample there, then we'll get diffraction and so on. So let's say we want to kind of tighten up on some of that resolution. So the typical resolution you'd get from a long pulse target station at a natural length with no real chopper system would be about 5 to 10%, something like that, delta Q over Q. And that's fine for about half the instruments at ESS. So those instruments that don't need good time resolution, small angle scattering, reflectometry, spin echo, imaging, and so on, that's fine. But if you want to do better than that in terms of resolution, then you're going to need some chopper system to select out your wavelength band. So let's do that. Let's put a little chopper here and only select out a small region in wavelength. So this wavelength band is given by delta t, this uncertainty here, or the pulse width. You can work through the algebra here, but it just goes as 4 over L2 pretty much. Okay. So if you plug those numbers into the previous example, you'll get about 1.8 angstrom. But you can see the problem is that the next pulse comes in, 14 hertz, but you can see there's a huge amount of the frame when it's not doing anything. I'm not counting neutrons. Okay. So that's inefficient now. So all of those gains that I've got from having this long pulse, I've now massively reduced them by putting in this chopper system to gain back some resolution. The other thing I could do is I could make the instrument much longer, but then that delta lambda will get smaller because your L2 will be getting so much bigger. So the very nice solution is what's called wavelength frame multiplication, whereas you have a chopper system that runs at some integer multiple of the source frequency. Okay? So in this case, I've got it running 3 times faster, and you can see that actually I'm going to select out different wavelength ranges and actually essentially fully populate the frame. Okay? So this is a very nice way of making an efficient instrument with good resolution. And so effectively, the other way you can think about it is you're effectively making the instrument shorter. Okay? So by having this multiple of 3 in this particular case, then the instrument can be 3 times shorter than what I would have to do if I wanted to get the same resolution, but with a much longer instrument. I do need another chopper because I need to make sure that it doesn't, you can see these choppers running at 3 times the frequency is opening at a whole range of times when I don't want it to be open. So I need to have another chopper, so-called frame overlap chopper, running at the source frequency and so on. So there is some more complexity. I have more complex choppers, need more of them, but it gives me a chance to get good resolution on a shorter instrument. So the moderator assembly that's going to be used at ESS is rather neat and is shown here. So here's a heavy metal target, which is tungsten. Okay. The proton beam comes in from the side. There's a water pre-moderator. That just really takes out a lot of the high energy neutrons. And then we have 2 moderators on the top, which are going to be water and hydrogen, as we'd said. So this is a plot of the moderator height, so that's its thickness, as a function of the brightness. And what's observed, I think the guys at JPark were the first people to really think about this, was that as you make the moderator smaller, so shrink it down, the brightness actually goes up. Okay? So rather than having a big face producing neutrons, you have a much smaller face of neutrons, but it's much brighter. Okay. And then there's some technical term here, which is the brightness transfer, which depends on the coupling between your guide, instrument, and the moderator, and so on. This is typically how the function looks as a function of height. You multiply these 2 things together, and what you find is that you get large brightness gains for small moderators, about 3 centimeters in height. Okay? So we're going to have small moderators. As you saw in the ISIS case, some of the moderators are so big, something like that. We're now going to shrink them down to 3 centimeters. So this is what the moderator would look like from the top. So proton beam would come in from the side here. Okay. So you're going to have hydrogen So you want parahydrogen, okay, not ortho, and also water. So you've got water pre-moderator and then you've got water at the side. So you can see with this design, and it's 3 centimeters thick in this direction. This I think is going to be 24 centimeters across, something like that. And so depending on the view that I take of the moderator, you can see I can see either a lot of the cold parahydrogen, or I can see the water, which is warmer, or I can see a combination of both. So I can tune the spectrum that my instrument sees depending on the view that it has of these two moderators. Okay. So yeah, so fully coupled, so all surrounded by a reflector. There's our beryllium. So really no compromises. Let's just use the proton pulse length to set the time structure, and then use the choppers subsequently to give us the right instrument characteristics. Use hydrogen for the cold spectrum, water for the thermal spectrum, and ensure that all the beam ports, as shown here, can actually view both of these beam ports. So this is a view down the axis. If you go off to the side, then you get a view of the water, which is here. You go to this side, you get a view of the hydrogen. So you can see, depending on the view you take, your instrument can get the profile that you want. So the boost at low energy neutrons, long wavelength neutrons from the hydrogen, or the boost for the higher wavelength, shorter wavelength neutrons from the water. So this is a rather nice, a nice feature of ESS, so-called bispectral extraction. Yeah, this is what the target will look like. So this is the wheel. Here's your reflector. This is where your beam lines viewed up here, so where your moderators are. And you can see you've got a 2.6 meter tungsten wheel. This is a big thing. It's sort of compartmentalized into different sections. It weighs 11 tons. It has a lot of very pure tungsten and rotates at a frequency of, I think it's just over 23 hertz. So this thing is relatively slowly rotating, and it's helium cooled. Okay, so it's really a huge engineering challenge. And that's all because you want to spread out the proton pulse. So you've already spread it out in time by the long pulse width, but you're also spreading it out by the fact that the target is constantly rotating round. Okay, so this is going to be a real challenge, actually. So these are the instrument suites. So 22 instruments. Find your own flag or institution on there. But let's just think about this. So clearly we've got a lot of instruments clustering out here. So anybody an idea about what this length is?
130.
Yeah. So these are all at that magical 157 or whatever it was we got calculated, because these will all fill the full frame. So that's the natural length of the instrument. Okay. So here we've got engineering beam lines, macromolecular crystallography, backscattering instruments, and so on that need resolution. Or if we're going shorter, things like small angle scattering. This is Loki, one of the instruments I'm responsible for. SCARDI, which is down here, small angle. Reflectometers, Freya, it's another one I'm responsible for. This is a STEER. So these are all instruments closer in. So you can tell straight away that they're not intrinsically high resolution instruments. They can live with the 5–10% resolution, whereas these guys are going to go use the full frame and use various chopper systems to get the resolution that they require. Yeah.
Can I ask a question to that?
Sure.
So the reason to be closer to the target is that just to save money on the neutron guides?
Yes. Well, that's a nice benefit of it. So you save on guides. So yeah, as I say, these are 165 meters, something like that. Shielding, and also chopper systems. The chopper systems on these beam lines are typically less complicated than the longer ones, where they're using frame multiplication. So yeah, the savings come from these instruments by ensuring that they're all the same length, so they all fit in one big building. Buildings are expensive as well. So it kind of surprised me when I first went to the Rutherford lab. I always thought the cost of a neutron instrument was all clever stuff. It was detectors, it was electronics, and so on. But actually, it's a lot of mundane stuff like steel and concrete, wax and things that you use for shielding of instruments. That's a huge cost. Guides are not so expensive considering how amazing they are, but there's a relatively small world capacity for producing guides. And of course, everybody wants guides now, so that's the challenge. So here's the instrument. Here's the first 8 that ESS are considering. And actually, this first 8 has been refined down to the first 3 beamlines that will deliver the first science that we mentioned. And I think in the current thinking, the first 3 are ODING, which is an imaging instrument, DREAM, which is a powder diffractometer, and LOCI, which is broadband SANS. So those are the first 3 instruments that you would expect to see in the first user program at the ESS. Okay. And here's a slightly nicer, different view, just showing all the lead institutions. So I don't know if any of you come from those institutions, but those are the ones that are leading on the development of these beamlines. These pictures are all, I had some new ones, but they're a little bit out of date, and this is from 2017. So this is the accelerator here, so this is a LINAC going straight in, so 2 GeV, remember, 2 megawatts into the target, which sits here. This is the long instrument hall. Okay, so this is out at 165 meters typically. This is where all the guides will run. Yeah, that's the accelerator. Yeah, this is the target station. The target will sit in there. Yeah, so the long instruments, we're going to be sitting in there with our small angle instruments. So it's a lot of concrete. I can tell you that. Actually, if you really want to know more about the instruments, obviously we haven't got time to discuss those today. But very recently, this nice review paper came out with a long list of authors, like it's a nuclear physics type publication or something. So it's a first for me. But actually, it's very accessible. It's open access. If you go and have a look at that link, which is in the slides, it's worth having a look. It'll explain some of the design characteristics and go into more detail than I've been able to do with the instruments. But yeah, here we are. Accelerator, target building, long instrument hall, office blocks, maybe? I'm not entirely sure what they are, and so on. I mean, have you been out to the site? Do you work there? Is that? No.
They show it to us regularly.
It's kind of mandatory, I think, if you go to London. Just
Pretty much.
Oh, super. So just to contrast, this is the Spallation neutron source in Oak Ridge. So this is the short pulse target station running at 1.2 megawatts. This is target power here. This is a megawatt. This is 1.2. This is 2009, so it's been running there quite reliably for quite some time. But the approach here is different. Rather than having a solid target, use a liquid target. So they use liquid mercury, so you can imagine that's got huge advantages. It's heavy, it's a liquid, so it's very good at transporting heat, which is one of the challenges here. So it's, that's very promising. Although it comes with huge technical challenges, which have only recently been controlled, I think it's fair to say. Part of the challenges are that when you put that much proton power onto a liquid mercury target, you can form bubbles in the mercury. And these bubbles collapse by sending supersonic jets of mercury over very small length scales. That's okay unless that bubble happens to be close to a surface. So what happens is the mercury kind of like little needles start sticking into the target containment and start to damage the containment vessel. But now that's in hand by the bubble helium and things in there to act like a bit like a shock absorber. And secondly, the point is many countries, including Sweden, don't want to have highly active liquid mercury. But you know, we're all used to working at facilities which have lots of risks, and we mitigate them down to make them safe. So interestingly, the SNS, which is running at 1.2 megawatts, has just received a significant tranche of funding to increase the power of its accelerator, and that's the first step on to them building the second target station. So much like we have at ISIS, they are going to have, in addition to their 60 hertz first target station, they're going to have a lower frequency second target station, which will be optimized for cold neutrons, much like second target station. So low frequency, you know that now because that gives you that large wavelength range, lots of cold neutrons. But whereas we run at 40 kilowatts, they're going to run at, on the second target station, I think it's something like 700 kilowatts. So 1.2 on the first target station, 0.7 on the second megawatts. Should be an amazing source. But that's not funded yet. But I'm sure it will be. It's a phenomenal neutron source. So you can see that with a combination of short pulse and long pulse, you're going to have all your neutron needs are going to be provided. So very quick summary. So short pulse, you get this nice intrinsic resolution. Okay, so you start with good resolution, and then you have to, you can only make it worse. Long pulse, you have moderate resolution, 5 to 10% typically, but you have such high power because you spread things out in time so efficiently, you can then use your chopper systems to win back some of that resolution. And you have this really nice matching of the accelerator to the target. By just spreading out that time scale, you can just spread out that power deposition into your target that allows you to go to the higher powers. On a short pulse target station, that's a real shock to the target, 50 times a second, every time it gets hit with this huge beam. Shielding requirements are a challenge because we're producing lots of hydrogen neutrons, but that's the same for a long pulse source too. And because these beamlines are typically going to be quite long, coming back to your point, 160 meters, there's beamline cost, just the length, number of chopper systems and so on. But what they have in common is that they're scalable, so you can keep adding more accelerator power, which means pretty much linearly more neutrons. You can run multiple target stations. Of course, the equivalent to a reactor is to run a guide hall off to the side. At a facility at the spallation source, you run a different target station. They're very flexible, and they are very efficient at covering Q omega space. So the momentum space and energy space is covered very efficiently with a spallation source. So if you want to survey large regions of energy and momentum space, then a spallation source is probably the technique that you want to do. So I said I'd just briefly talk about compact sources. So compact sources are typically where you take a beam of protons, accelerated up to relatively low energies, so a few MeV, between 2 and 50 let's say, and bring them onto a very light target like lithium or beryllium. And actually it's rather inefficient. So you're getting something like 10 to the minus 2 neutrons per proton. So, so you're not getting a huge flux per proton, but actually they can be highly optimized. So this is a figure taken from the report on Jülich for their high brightness source. And now this becomes something that's a bit more tractable. So a spallation neutron source is a big laboratory, a big facility. Maybe this is the kind of size that a large university might be able to host. So you can run a range of instruments, so you won't have the performance in terms of ultimate neutron flux, although you can do pretty well. But what you'll have is a huge capacity. You'll be able to develop the community, both academic and industrial, by just giving lots of access to neutrons. One of our big challenges in the neutron community is there are relatively few neutron sources around the world. And some of you will be aware that a lot of them are closing, or have closed. Norway, Germany, Paris, and so on. So anything that we can do to build up the neutron ecosystem, if you like, is a really positive thing. And compact sources such as this, I mean, they're still big sources, let's be honest about it, but are clearly part of that ecosystem. Okay, so let's, how long do we have? 10 minutes maybe? Let's run very quickly through then just some of the techniques. So diffraction, let's look at diffraction. So we're going to use time of flight. So target, moderator, let's call it the moderator, sample, detector. Okay, so the nice thing here is that in a single detector you measure the complete diffraction pattern. Yeah, and the reason is because you're using time of flight. So you're coming in with a range of neutron wavelengths through a single angle, means you get a complete pattern in a single detector, so at a single angle. So let's have L1, the distance to our sample, L2 to our detector. The d-spacing is going to be directly proportional to the time of flight of the neutron. You can go away and measure this, and work this out. It's not particularly difficult. Yeah, okay. So very straightforward. Single detector. Use the time of flight to give us a diffraction spectra. Of course, we're not going to have a single detector. We're going to have as many detectors as we can because they're all going to have different resolution, and we can use that to then focus these different detector banks to give us intensity and to play around with resolution and so on, depending on what we want to do. So the resolution, how do we calculate resolution? Well, it's going to be related to the uncertainty. Okay, so we've got uncertainty in the angular spread of the detector. Okay, so a delta theta, if you like. We're not entirely sure what the angle is. Timing error in the electronics. That's going to be really small compared to everything else. And timing error is due to the flight path uncertainties. So, of course, one of the uncertainties is quite when the neutron was produced. So when you've got a short pulse, that's a relatively small number, but the long pulse can be quite big. So when you plug all those numbers in, you assume they're Gaussian independent, you add them in quadrature, and you get something that varies on the uncertainty on the lengths. Well, let's assume you've got good surveyors, so that's going to be small. Uncertainty in the angle, so basically differentiating Bragg's law, which tells you that for backscattering you get really good resolution. Okay, and then a small error in the timing, which on a short pulse target station is going to be a relatively small contribution. Okay, so what you can see is that if this is delta D, this is your resolution if you like, you can either increase the scattering angle, so go towards backscattering, or you can increase the length of the instrument. So an example of that would be HRPD. This is the world's, I think it's highest resolution neutron diffractometer. Maybe JParc has something similar. But you can see why these guys stuck out here. So most of our instruments are relatively short. This is kind of 20, 30 meters. Okay, this is HRPD out at 120 meters. And that's basically to take advantage of this thing here. Okay, to give you the highest possible resolution and then to run at high angle as well. Okay. Alternatively, this is WISH, which is one of our other diffractometers. This is on the second target station, sits here. Any of you used WISH? Yeah, good experience? Yeah. It's an amazing beamline, amazing team. So this is what I was talking about, is when you try and populate it with as many detectors as you can. So we have two large banks of detectors. These are position sensitive. Okay, so they sit in the horizontal plane. L2 is quite short, 2.2 meters. And we have pixels up here, something like 8 by 8 millimeters in size. So I think you're even generating more than this. We're getting to the big data world, several gigabytes per run. But what that does is you have an instrument with very good resolution, good flux, and incredibly low backgrounds. And just as a way of showing that, this is some of our work from a little while ago, where we basically wanted to look at a thin film antiferromagnetic semiconductor that you can only stabilize in thin film form. So rather than having a bulk crystal of however big your bulk single crystal is, this is a single crystal, but it's only a few tens of nanometers thick, sitting on a massive substrate. So all the diffraction comes from the substrate, but if you look carefully, you can find the scattering from your film, which is tiny compared to the scattering from the substrate. But it's separate in Q, so that helps you, but it also shows you the flux and background that you get on this instrument. By measuring various Bragg peaks, you're able to solve the structure that you could not do by any other technique. Okay? And that's a combination of high flux, good resolution, low backgrounds. That's what you get on a spallation source. This is just another example from HRPD, which is where these guys were looking for incredibly small distortions from a cubic to a tetragonal structure in meteorites. The reason they're interested in meteorites is that these have some amazing magnetic properties, and if we have a world where we need to be concerned about rare earths and so on for our permanent magnets and so on, if you can do it with something as simple as iron and nickel, which meteorites can do and nature can do, that's really useful. The problem is the reason that these have these unique properties is they take up to 1 billion years to cool. That's difficult from an industrial process to justify spending money on something that takes 1 billion years. So these guys have been trying to accelerate that process in the lab, And they're making some good progress. So they've got the tetragonality. So the C over A here, you can just see how small it is, but you can see the resolution in the measurement. So that's HRPD going a long way away. But they haven't got it quite right yet, because whilst they have the tetragonality, they've also introduced some site disorder. So the meteorite, the iron and nickel are very highly ordered. It also means, because it's the pulse source, that you can use things like pulse sample environment. Okay? So in this case, you know, a conventional magnet on a conventional source, I mean, there are higher examples, but including here, but 14 Tesla is not a bad field for a superconducting magnet in steady state. On a pulse source, you can use pulse magnets. So you can do 30, 40 Tesla and pulse the magnet to coincide with the pulse of the synchrotron on our spallation source. Okay? So that means you can do measurements in much higher fields than you can do, again, because it's a pulse source. You can do lots of engineering studies. So this is one of our beamlines that combines combines imaging and diffraction. So you get atomic scale structure and also do imaging, which these guys have applied to a range of systems. So one of the things they've been doing is in agri-food, looking at root systems. And oh, sorry, I think that's killed my laptop. Let's try again. That's disappointing. Hang on then. Oh, did it come back? I just wanted to show you this because it's fun. This is some data from, literally, from one of our instrument scientists, Dr. Genevieve Burka. She went to the dentist with a problem with her teeth, had a wisdom tooth removed, asked the dentist if she could keep the tooth. And so, of course, as you naturally do, you image it on the beamline. And this is the power that you can do with neutrons now. You can actually do imaging, and of course what we're using here is because we have a band of neutron energies, we can actually look at the energy dependence absorption of a sample and not only get the spatial resolution from our detector, we can actually use the energy dependence to look inside these samples as well. So yeah, how to experiment on yourself without any ethical issues. Right. Okay. So I'm aware that time is pressing on. Let's just have a look. Let's just have a quick look at spectroscopy, and then we'll conclude. So, having said we want to look over different length scales, we want to look over different energy scales as well. From the quasi-elastic, where we're looking at incoherent motions of individual atoms, molecules, and so on, through to the collective modes, whether they be phonons, magnons, and so on. And the way we do this is that for elastic scattering, of course, we're assuming that the neutron energy doesn't change after the scattering process. Okay? But this is not true for an elastic scattering. So the neutron can give energy to the sample and create excitations, or it can annihilate excitations and come out with a higher energy. Neutron detectors are energy insensitive, so we've got to use something else. And there's something else we're going to use is time of flight. You could use crystals to select out a particular energy, but that's efficient on a reactor, but it's not so efficient on a time of flight source. So the way that we do it is to use a so-called Fermi chopper, and there's various ways you can do it, so-called direct or indirect geometry. I'll only have time just to talk briefly about the direct geometry, and for that what we're going to do is monochromate the incident beam, or loosely monochromate it by a Fermi chopper, unlike using a crystal on a reactor. And so this is your Fermi chopper, which is basically a set of rotating blades, and actually if you sync the rotation of the blades to the pulse, it becomes a little bit like a sloppy moderator, if you like. So you can tune the energy resolution you get by the slit width and how fast they turn. So that didn't work very well, but they should rotate such that only a certain neutron energy can pass through. Okay? And that depends on, as I say, the slit width and the rotation speed. So rather than using crystals, which have various characteristics that are, again, not particularly suited for spallation sources, what we can do is use our Fermi chopper. Okay, so let's just look very briefly at our distance time plot. So here's our moderator, here's our chopper, our Fermi chopper, here's our sample, and here's our detector. Okay, so here's our pulse from the source, here's the spreading out of the energies. We're going to use a chopper to select out a wavelength range. Okay, and then it's going to interact with our sample. And if there's no energy transfer to or from the sample, then it should come out here with the same gradient. So that's elastic scattering. Okay. If there's now some inelastic processes in our sample, then that will change the final energy of the neutron, which will change the time it arrives on the detector. So in this case, you can see here the neutrons are slowing down. So they've given energy to the sample, so created excitations. And in this case, they've taken energy from the sample, annihilated samples. So these are speeded up, and these are slowed down. So this is how it looks on the time distance diagram changes as you move along the beamline. But let's just have a quick look how this looks. We don't need to worry about energy resolution. So this is how such an instrument looks. Here's Merlin. Here's the instant neutron beam. Here's our chopper. So there's a T0 to take out that initial burst of neutrons. Fermi chopper, the sample. Here's our detector tank. And this allows you to cover a very large range of Q omega space. You can use rep rate multiplication. Sorry, I didn't have too much time to talk about that. But this allows you to just establish these really beautiful figures in four-dimensional space. The 3 dimensions of Q and energy of these complex, in this case, magnetic systems, to you get a full access to the Hamiltonian. Okay. All right, let's just finish on something that you might be interested in if you fly a lot. So having said that, what you don't want to do is see these very high energy bursts of neutrons. What you want to do is look at the moderator, the milli-electron volt neutrons. We produce a very large flux of high energy neutrons, so sort of 800 MeV neutrons. It turns out that's very similar to the spectrum you get in the upper atmosphere, which generates a lot of high energy neutrons. Okay, so we're probably being hit every now and again, every once a second or something, by a high energy neutron. Okay, doesn't seem to do us too much damage. We've kind of evolved to deal with it. But actually, if you're in a plane flying at 30,000 feet, high energy neutrons can interact with microelectronics. Okay, and they can damage microelectronics, or they can flip bits in microelectronics, which if your plane is being controlled by these bits, you probably don't want them flipping around randomly. And so you need to understand how robust are your microelectronics against these so-called single event effects, where a high energy neutron comes in, does something in your electronics. That's important in planes, but of course the next frontier is autonomous vehicles, and even though these effects are very rare, when you scale it up by how many autonomous vehicles you're going to have on the planet, you need to be worried about this. So by looking it straight into the heart of a spallation source, looking at mega electron volt neutrons now, essentially you can do accelerated testing. So 1 hour in a high energy source on a spallation facility is the equivalent of something like 100 years flying at 30,000 feet. So this allows manufacturers to do accelerated testing of microelectronics. And so this is really something new that we're doing at the lab. But you can only do a spallation source because you have those high energy neutrons. Okay, so just to summarize. So time of flight that we get from a neutron source is well matched to surveying these very large areas of Q omega space. You can get flexibility by running through multiple target stations and design of your instrument. It's a scalable technology, so we know we can add more and more power within reason. And very much the work I've been talking about complements what you can do at reactor-based facilities. And similarly, as we shall see in the coming years, hopefully long pulse also complements short pulse. You need the kind of combination of both. And I think there's a very bright future, whether it's ESS, whether it's compact neutron sources, or maybe even the next generation sources, which are maybe completely different to spallation. I'd like to just finish by thanking all my friends at the Rutherford Lab, at the ILL, and all these people here, and to thank you for your time and attention. Thank you. Any questions? Yeah, sure, sorry.
What's the advantage of using muons over neutrons? What sort of
Oh.
can you actually do?
So it sort of depends what kind of things you're interested in. So muons are very good at seeing very small moments. So if you're interested in magnetic systems, you can see moments, hundredth of a Bohr magneton. Whereas with neutrons, tenth of a Bohr magneton, and so on are bigger. So if you're looking for very small moments that you might get in a symmetry breaking superconductor, or if you're looking above a phase transition where you've got fluctuations, so muons are very good at that. They can be very good at studying ionic motion, so in batteries. So if you want to study lithium or sodium diffusion in a battery, an example? I don't know. I'm not sure I have time for this, but basically you can see when the lithium ions start to diffuse in a system. So you can see where they're frozen, you can see where they move. So you can establish very reliable values for diffusion constants and so on, which you can compare against other techniques. And the nice thing with the muons technique is that they don't get affected by things like grain boundaries. Whereas if I understand correctly, if you're doing things like impedance spectroscopy, you have to worry about grain boundaries as your ions diffuse around. Whereas muons are not sensitive to that because it's a local probe, but you can see this ionic diffusion. So very good as an analogous particle to hydrogen in systems, light elements, diffusion, and very weak magnetism.
They don't actually diffract, they just kind of fuel.
Yeah, exactly. That's a very good point. They don't diffract, they don't scatter, they implant. So, so you have to know what site they go onto, because in a complex crystal structure, maybe there are various sites, but you can calculate with some confidence where those sites are. Then they diffuse. Or the other thing is they in the case of positive muons, they can actually grab an electron, and they become like a new element, which they call muonium. So people study the chemistry of muonium as it interacts and so on. But if you're a solid state physicist like I am, you kind of don't want to know about that. You just want to know what the local field is in your superconductor, let's say. But you have to be aware that sometimes things can be changed by the fact that it's not a passive probe. Neutrons, by and large, we think of as a passive probe. They don't damage systems. The muon doesn't either, but it does interact with the system in a different way than a neutron beam does. But there's even fewer muon sources around the world. There's PSI, there's ourselves, there's Triumph in Canada. But it is an amazing technique. Okay. Oh, one last question then.
Quick question: how big is the loss over 150 meters of beam guide?
Oh gosh, how big is the loss?
Or are those ballistic guides, or are they?
It depends. So it depends on so Wish, for example, is a ballistic guide. I can't honestly give you an answer. My suspicion is it's very low. So the reflectivity of guides depends on many things. Well, no, is it going to be very low? The reflectivity is sort of well over 90%. But if you've got to have multiple bounces, then you're going to lose. But the important thing with neutrons is not only the signal, it's also the noise. And so by getting far away, your noise levels drop down. And so whilst you may have losses due to guide misalignments and so on, you win in the efficient transport more than you lose. All right. Thank you for your attention. I'll see you tomorrow.